So let's go over chapter 2. This is kind of a short chapter. In class, we're watching some videos and stuff, and this is just really now to get starting into the meat of the class. Some of these concepts that I'm going over in this chapter, we will see again, so don't panic if this is really new to you and you think, oh my gosh, I'm got to figure out how to calculate moles. And we'll go over that. I'm actually planning to do a demo in class where we'll actually calculate moles and that kind of thing with actual substances in class. And we'll, because I want it to be more hands-on instead of me just telling you how to do it. So we will do that. But right now in this chapter, we're just getting into the start of the chemistry, all right? So we'll just go through this and we'll very slowly get into it. And I think it will be fairly straightforward once we get there. All right, so this chapter is based on atoms, and clearly we are going to, again, come back to this because we are going to the nuclear power plant. So we're going to talk a lot more about isotopes and all of that sort of thing as well. So let's get going with this. Put it to full screen. So atoms. So this is going back to a little bit about what I was saying in the first class, talking about philosophers and how they sort of understanding the world around them. And so initially, when it came to atoms, of course, it was impossible to see them. And they didn't even have microscopes way back when a lot of these philosophers that we like hearing these names like Aristotle and that sort of thing, and Plato and all of these famous philosophers that we know are philosophers. We might not know what they did because what their thoughts were on how things work have been passed down through ages, right? So, but this goes back to the idea where, you know, these philosophers would sit around and basically argue about what they thought the world, how the world worked, or how it was made up, and they didn't do experiments, and that was, and we'll talk more about that. So, at the beginning, it was one of the things of what are things made up of, and the first two philosophers that are given credit for actually having being on the right idea was actually Democritus, and he had. Someone who came slightly after him is Leucippus, and you can learn more about these two individuals and how they were related to each other in terms of their thinking in your text. But basically, they both, well, Democritus was the first, and then Leucippus continued his thoughts. And their thought was that matter is made up of very small individual particles. And so they were really the first ones to come up with this idea of what we now call the atomic theory. And they had this word called atomos. And that is the point at which matter can no longer be divided. And so the argument came from, and as you can see here, if you look out at a beach and you see water and you see sand, if you look at it from far away, they both look continuous, right? The water looks continuous and the sand looks continuous. But as you get closer and closer, specifically the sand, you can see with your naked eye, that it's actually made up of tiny pieces. And some of those pieces can be really, really small. And with water, it's harder for us to separate that, but they were thinking in terms of drops, right? So smaller and smaller drops of water, because they didn't know how small that this could actually get, right? So, so you can see the idea of an atom per se has been with us for more than 2,000 years. All right, so these people were you know, from the BC period of time, right? So, but of course, since these guys were arguing, they were arguing because that's what these guys did. Democritus was a contemporary of Aristotle, and they disagreed with each other. And have you ever heard of Democritus? Probably not, right? But Aristotle, probably so, right? So you can tell who won the argument, right? So Aristotle, on the other hand, said that instead of being made of indivisible particles of some kind called atoms, like Democritus was saying, Aristotle believed that that matter was made up of the four elements: earth, air, fire, and water. And that's how it was. And he clearly won the argument, because that's why we all have heard of Aristotle. So at the time, and his point of view had persisted for a very long time. And everyone thought that Aristotle's view was correct, until we got another scientist, or another philosopher named Robert Boyle. And Robert Boyle, and there's others. I was actually but discussing this with the physics guys the other day, in terms of who was actually doing experiments first. But Robert Boyle, you can see here, he wrote this book called The Skeptical Chemist. And he wrote this book back in 1661. So you can see that Aristotle's view predominated from, in the BC times all the way up until the 1600s. All right. But it wasn't until Boyle, he actually started doing experiments. Right. So I'm going to just read this off. I did this in class. Like he's considered the pioneer of modern science. And he insisted that you could explain these natural phenomena by actually testing things, right? So he actually wanted to do experiments. So this was really a real break from alchemy. And he believed that the elements could not be broken down into simpler substances, all right? So this is, I lift this off. You can see the link here. There's a lot of stuff about Boyle if you're interested. So even in his time, as you can see, the idea of doing an experiment was like, what are you doing, right? The way they discovered things, right, is to argue and use logic, like Aristotle and others had worked out. But Boyle, he was having none of that. He was more interested in drawing his own conclusions from what actually he observed. And he did all kinds of experiments. And he started publishing his work, not publishing like I would publish stuff, but sort of. I mean, there was no peer review. There was books, and then they would argue it out some more. But he was hard to argue with evidence, right? So he published works on philosophy, medicine, and religion. So all kinds of stuff. So he was a philosopher, but he really believed in experimentation. So with him started to come laws. All right. So, based, in philosophers or scientists now, I guess we could start calling them scientists, they would actually start doing experiments to try and understand how the world was working. And one of the first scientific laws is called the law of conservation of mass. And we're going to be playing around with this one in lab. So here, law of conservation of mass. And now it seems, you can't get something out of nothing, and you can't destroy matter. I think these are things that we kind of know it's sort of almost intuitively now, but this was how it works, right? So law of conservation of mass, Antoine Laurent Lavoisier was the person who, he has to speak French, Antoine Laurent Lavoisier was the person who solidified this law. And basically, what would happen is if he would start off. So if you started with mercuric oxide and you had 100 grams of that, and you broke that down into mercury and oxygen, you would not destroy the amount of mass. You would have continuous. You started with 100, whatever amount of mercury and oxygen you get, if you add those two masses together, you're going to come back to 100. So that is the law of conservation of mass. All right. So basically, there's nothing going to happen here to the matter, even if it is going through a chemical change. You still have to have the same amount of matter, right? The next one is Proust's law, or the law of definite proportions, okay? And here, what we have is that when you have a compound, so now when you have more than, two elements put together, two or more elements put together, okay, they're always going to be combined in definite proportions, all right? You're not going to get fractions of proportions. You're always going to get these definite proportions that these elements are going to come together in, all right? So an example of this would be called the Berzelius experiment. So here, if you're making lead sulfide, for example, you have 10 grams of lead and 1.55 grams of sulfur, you are going to get 11.55 grams of lead sulfide. Now, if you started with 10 grams of lead and 3 grams of sulfur, you're still going to get 11.55 grams of lead sulfide, and you're going to have some leftover sulfur. All right. So these things can only be combined in certain amounts, and that's how it works. So this is the law of definite proportions. So if you think of H2O, so you've always got 2 hydrogens for 1 oxygen. So whatever you know, they're always going to be in these definite proportions, and they always come into these whole number ratios. All right, and that brings us to Dalton. John Dalton, he has this law of multiple proportions. So it doesn't mean that you're going to get a certain compound in more than one proportion, but what he's saying is that however, you know, these elements will always combine in certain proportions, but you can have 2 elements combine in different types of proportions to get different types of compounds, depending on how much you've got, basically. So think of carbon monoxide, CO, or versus carbon dioxide. So if you have carbon monoxide and you keep adding more and more oxygen, to a certain point, you're going to have leftover oxygen, just like we were just showing in the law of definite proportions. However, if you get to that magic amount of oxygen, all of a sudden you're going to mix CO2, so you're going to get carbon dioxide. Right? So here, the same thing here with the idea of nitrous oxide, nitric oxide, and nitrogen dioxide. So if you're combining nitrogen and oxygen, and there's a reason that we're all using gases here. We're going to come back to that later on, I think, in the next chapter. But if you're combining them, if you have, you can have them combined with 2 to 1, or 1 to 1, or this other one, 2 to 1 over here in terms of nitrogen, you're going to get a different compound now. These are different compounds with different properties. Okay, so it's not breaking the law of definite proportions, but John Dalton was saying that you can combine these in different proportions and you can get different types of compounds out of that. All right, so that's John Dalton. And John Dalton, of course, is also famous for atomic theory, and he wasn't quite right, as you'll see, but he really is the contemporary to what we were saying back here. So I'll go back here, right? So go back here, the modern version of Democritus, all right? So, and that would be John Dalton. And he was saying, okay, here you've got his multiple proportions, and here you can see how that's put together. This is sort of a visual, so you can see the differences between how nitrogen and oxygen can combine. But he, of course, was the person that came up with atomic theory that we use now. It wasn't quite right, but he was saying that atoms are made up of these hard spheres. And the reason he said this, and that, you know, because he could see that these different types of atoms would be combining in certain proportions to give different compounds, you would never get something that wasn't a whole number, right? You can see you have 1 to 1, 1 to 2, 2 to 1, 2 to 2, or 2 to 5, but you'd never get something like 1.75 to 1, or 1 to 2.430, or something like that. It would never be that. So this, because of these observations, he suggested that these atoms are actually these hard spheres, and you can't break them down, and they're always the same. Okay. Now, where he was a little off is that he didn't know about isotopes, and we're going to talk a little bit about them later. But basically, different elements, such as oxygen, as you can see here, they can have slightly different masses, because what you have is that you have, and we're going to explain this later, but basically there's different numbers of neutrons in this oxygen in these different oxygen atoms. But he didn't know about isotopes, and we're clearly going to talk about these later. So he was pretty on spot until later on we learned more about the atom and we learned about isotopes. So that was the one thing that he didn't quite get at the time, and we are going to talk about those later. Okay, so in my notes I wrote down his 4 main claims to fame. So first of all, matter is, Dalton we're talking about, of course. Dalton said that matter is composed of extremely small particles called atoms, and that goes right back to what we were saying before. And then the other idea is that he said that atoms of a given element are alike and differ from the atoms of any other element. And that was where he was a little off. So that depends. And that, except for isotopes, I wrote down in my note, and we will talk about those later. Compounds are formed when atoms of different elements combine in fixed proportions, and a chemical reaction involves the rearrangement of these atoms. So all of those 3 points, A, C, and D in my notes were correct. It was just a little wrong with B. All right, but he is credited with modern atomic theory because he was the one that now said this is how it is, and that's how it went. Now I start to introduce the idea of mole, molar mass, molarity in this chapter, and we are going to come back to that. We have a whole chapter on how these things are combined, but I want to give you a bit of history as to where this came from and how it develops. So there's another chapter where we'll actually talk about that, but I'm going to introduce it now because it's important, and it's also in this chapter. All right, so just to start off, what is a mole, right? What's a mole? And I know you probably have seen this crazy number, 6.02 times 10 to the 23, right? So a mole is just a measurement of a number of something, just like a dozen is 12 eggs, right? Or 12 of something, right? A mole is 6.02 times 10 to the 23 of something, all right? And this is called Avogadro's constant or Avogadro's number. Avogadro was another scientist. But where does this crazy number come from? All right, why do chemists use moles? Why do we do this? Now, the reason this comes from, and this is why I handed out the periodic table to you, and I hang on to those periodic tables because you guys are going to need them. Not that you're going to memorize it, but I want it there for you, and we're going to slowly learn about how it works, okay? Now, think about this. If you're a chemist, you cannot weigh out 12 atomic mass units of something, right? So if I go here and you go to the periodic table, this is sort of jumping. We're going to go back to this kind of idea later in the semester or later in the course. But you've seen this before, so I'm going to go back and explain where it comes from. But if you're looking at a mole and you see carbon here, carbon 12, right? We'll learn later this is 6 protons and it has a mass of 12.01, and where that comes from because there's different isotopes of carbon. But basically, if you look at it at the atomic level, it has a mass of 12 atomic mass units. Now, are you going to be able to weigh out 12 atomic mass units of something, of carbon? Absolutely not. You can't see it. As you know, we'll talk a little bit about the size of an atom later on in a few minutes in my presentation. We did it in class, right? So you can't measure 12 atomic mass units, but it would be much easier to weigh 12 grams. You can see 12 grams of carbon, okay? So chemists use the mole because, and it was worked out using carbon, because it works out to be the same mass in grams to match the atomic mass units. And it just so happens that if you weigh out 12 grams of carbon, you have 6.02 times 10 to the 23 atoms of carbon. And the way it worked is that if you weigh out a mole of anything, you'll always have 6.02 times 10 to the 23 of that. Anything meaning any other element, or as you'll see, any molecule. So if you have, I can't remember the molecular weight of water in my head right now, so that'd be oxygen is 16, so 16, 17, 18. So if you weighed out 18 grams of pure water, you would have exactly 6.02 times 10 to the 23 molecules of water. All right, so we're going to do some of that later on in the semester. We're going to do it in class, not even in lab. We're going to do it in class so that you can kind of get a feel for this. All right, and you know this course doesn't have tons of math, but this is a very basic idea that I'd like you guys to grasp. Okay. So this is why chemists use moles, all right? Because you can see them, right? So let me go back to the presentation here. So go big here and hang on to that periodic table, right? Put it in your book or whatever. So molar mass, what is it? Well, the number of atoms in one mole, right, is a mole of the atom, and it is in grams, its mass in grams is the same as its elemental mass, okay? So this is why this works, right? So 6.02 times 23 atoms is 1 mole of the atom, and 1 mole has a mass in gram that matches its atomic mass in atomic mass units. Okay, so that's where this comes from, all right? It's not because chemists felt like using some crazy number. They just wanted to make their life easier so that they can measure things out, okay? So now, where's the idea of concentration? So that's molarity, all right? So molarity is how many moles that you have in a liter of some sort of solution, okay? And it's measured really accurately using a volumetric flask. There's only one line on a volumetric flask, and you look from the bottom of the meniscus, and you have exactly 1 liter, and you have exactly, you know, whatever number of moles in there, and that is the molarity. So that is concentration, because most of the things that we deal with are actually in solution of some kind, all right? And again, we'll talk more about this later in the semester, okay? So now I'm just planting the seed so that you guys can recall that later on. So what is molarity? Molarity is a measurement of the concentration. It's the number of moles in a given volume, and the standard is a liter, right? Because we're dealing with metric. Now, elements, right? We're just talking about elements and how we have atomic masses. We're going to go over the atom later on in the semester. But remember, I just gave you a periodic table, right? So where did that come from? Well, this came from a scientist named Dmitry Mendeleev, and he wanted to organize things. So scientists like to organize things so that we can work together. And what he did is that he arranged his elements in increasing atomic mass, right? So we're just talking about the atomic mass. We'll explain later what that is, but I'll let you know now. It's the, you know, from the number of protons in those atoms. And he arranged them in order, right? And when he started doing this, we didn't have all of the elements yet, okay? But he was able to arrange them. And he noticed that when he did that, that there seemed to be repeating patterns in the properties of those elements. So he's essentially, and then he put those into different, you know, rows and columns, and as we'll find out later, we'll talk more about it. But as he did that, he was able to predict properties of elements that hadn't yet been discovered, right? Because he could see that all of these ones that had certain masses would have certain properties. Okay, so, and then later on, when those elements were actually discovered, they found that his predictions were correct, which was, you know, really affirming in that we kind of understood how things were working in terms of we as human beings, okay? And that's when his discovery, or his periodic table, was much more well accepted. The ironic thing is that he himself did not believe in atoms. He just wasn't convinced by Dalton's model of these hard spheres. He just wouldn't go for it. And later on, of course, he came around. But basically, when you look at your periodic table, you get this atomic number, you know, and as we'll see later in the course, the number of protons. The atomic mass, there's going to be a little bit of fudge factor here, because some of those elements are going to have isotopes, and we're going to go over later on what those are, all right, what are isotopes. But basically, there's different numbers of neutrons, and we'll go over what protons, neutrons, and electrons are, right? So this is what you're seeing in your periodic table. And in terms of, you know, what kinds of properties, and you won't understand all of these yet. Some of these we'll talk about later on in the course, but electron affinity and ionization energy increases from left to right. Metallic character, the most metallic are down here in the bottom left corner, and the least metallic are on the upper right corner. And atomic radius is, you know, this is the actual radius of, you know, anyways, we'll talk about this later because it increases this way. So he was able to see these. And just so you can see an example, this is from your book. And remember, you have the e-text available to you. So say, for example, for germanium, he didn't call it that. That's what it was. Winkler, a scientist named Winkler, was credited with discovering that in 1886. But 1871, Mendeleev predicted that there would be an element with an atomic mass of 72, said its density would be 5.5. He even predicted the color, so it had a dirty gray color. And then there would be some sort of an oxide of that element, and he predicted that it would be 4.7. Okay, so the density of the oxide, and then a chloride, because oxygen and chloride was what they did there. So the boiling point of chloride, he estimated it would be below 100 degrees centigrade. All right. So then Winkler actually discovered the actual element, and he found that the atomic mass was 72.6. That's pretty good, right? 5.47 for its density, so round that to 5.5, grayish white, right? And lo and behold, here's the density of the oxide, 4.703, and the actual boiling point of the chloride, 86. So that's pretty impressive, right? So based upon the predictions of Mendeleev, you can see how close he actually was. So like I said, this really made the atomic, the periodic table the way to show things. And over time, it has predicted many different elements, and even some that are man-made, it was pretty spot on. So it was pretty amazing achievement for someone who didn't even believe that atoms were real. Now, so on that point, atoms are really very real, and we watched this video in class to show how we're actually now able to see the atom. It was always hard to prove something you can't see it, right? So if you're like Boyle, you want to, proof is in the pudding, right? But now we're at the point where we can see it, and the reason was because they're so teensy tiny, right? And here you can see some examples I have on my slide. You can sort of see the radius of 5 atomic mass radii, really, or angstroms, sorry, angstroms. So you can see how tiny these guys are. And how do we see these? Well, combination of X-rays, different types of electromagnetic radiation, lasers, femtosecond lasers. These are, well, I used to use one. They're really high energy lasers, very damaging. I would never even think to put my hand in laser path, but it would burn a hole right through me. But these lasers have very, very tight wavelengths, very concentrated energy. You can even use them to pick up atoms, as you saw in this video that we showed in class. Okay, and then in this one we were looking at that nanoparticle, and you could see the applications that are available based upon the positioning and inconsistencies in the layering of these atoms. And there's a lot of work going into this kind of thing now. So if this excites you, I really want to stress that this is a place where you can easily get a job in the future, because this is where things are. And that's why I wanted to talk about it in class. Now, another thing that I can introduce in chapter 2, and I had mentioned in one of the first lectures that each of your chapters, well, most of them, not each one, there's a section on green chemistry, and I'm going to try to hit most of those in this course, because that's sort of the point of this course. It's contemporary, so we need to know what we're doing with our chemistry, and one of the main things is recycling. And so in this point in the book, they sort of introduce the idea of sustainable or non-sustainable recycling. So if you're talking about something that's not sustainable, right, you're going to still recycle this way. So if you take your can, it's, the iron ore here is one of the basis of this. It makes into the steel, right? So hematite, the iron, is actually produced into pig iron. We're going to talk about this later when we talk about, I think Earth is the chapter. We're going to talk a little bit about mining. But this is converted into steel, and we're going to talk about what steel is later in the semester. But basically, this iron will eventually go back into the environment, and it can be incorporated into living things, okay? But it's actually not, it's not sustainable to us as human beings, because we're still going to want more cans. So we're just going to go and mine some more. It's going to be easier to mine some more than get the iron out of these fish, right? So in terms of sustainable recycling, right, one great example is, the industry we have of recycling steel and iron from cars. So after your car is done with, and mine's almost at 200,000 miles, so it's getting close. but it's still running. So eventually it will be recycled and it will be made into a new car. And there's a really well-defined industry in doing that. So this is what we would call sustainable. And then we don't need to mine as much iron because we can then recycle it. All right. So this is the idea. Now, the other thing that I'm going to be talking about a lot is green chemistry. So I'm going to get into that in a sec. I showed you this video about what happens when we recycle at home, right? So the different streams, places where you can sort into paper and then everything else. Whereas, like I think I mentioned this in class, in my where I am in now in Pompey, I just live outside of Manlius. So we have recycling, which is dump everything into the same container. I think I mentioned in class that I used to bundle my paper even and put it into the bin, and now I know better because I was studying this for this course, and I was like, oh, I shouldn't be doing that because they need it to be light so that they can separate it. So, but then there's other aspects of recycling that you might not think of. And I myself, a lot of the clothes you see me wear are actually used. I don't like to buy a lot of new clothing. I believe in recycling clothing. The idea of donated textiles, because so much goes into the landfill. This is my putting myself on the soapbox here. So much of the landfill is just recycled textiles, and these can be not recycled. Textiles go into the landfill. Why not recycle them? When you donate your clothes, there's people that know how to do this, right? So if you donate your textiles, anything, even old bed sheets, towels, anything. 45% is reused clothing, right? Someone like me, I'll go and buy it if it's if I can use it. Some of it is going to be converted fiber, and some's going to be made into wiping cloths, right? So, for example, T-shirt, if it's stained, no one's going to want to buy that, right? You don't want to send that to somebody, just because they can't buy a new T-shirt doesn't mean that they want it stained, right? But the cool thing is that it can be converted into a wiping cloth. Socks can be converted to pillow stuffing, right? Of course, it's going to be cleaned. You're not going to be sleeping on someone's stinky socks, right? So they're going to clean the fiber and recycle it into pillow stuffing. Denim made into household insulation. Teddy bears, I hope that never happens to my bears, but teddy bears converted to car seat stuffing. Bath towels, wiping cloths, right? So this gives those textiles some other life. Also organic materials. It's not so much here, but where I'm from, there's recycling days for food waste, and that is going to be composted and reused in that way. Unfortunately, that doesn't seem to be a popular thing here yet, stateside, but it's much more popular, at least around where I'm from, around Toronto. So when I go to visit my mom, we recycle our organics, all right? So these are things to think about. Now, and as I said, we'll talk more about this in the semester. So again, some of Chapter 2 is still setting up some of the course, even though we're getting into chemistry. But yes, the green chemistry, you're going to see every chapter in your book. And again, remember you got the e-text is talking about green chemistry. So if you're interested in this, definitely get into it. And we spent some time in class talking about it. What is it? So when you really distill it down, it's a way of replacing rare substances with more abundant substances, and a way of replacing hazardous materials with less dangerous substances. So those are the two take-home messages, okay? And really, if you could recycle some of those into your chemistry, makes it even greener, right? So you can see some notes in that I have on page 5 of my notes. So like I said, they're trying to replace these very rare elements. Specifically now, a lot of research looking at your computers and your hybrid car batteries with more abundant options and less damaging to mine. So thinking of lithium, for example. And sodium chloride, much less hazardous than using lead, cadmium, and mercury, right? And as you know, you probably know this, right? Lead was removed from paint and gas. That's why gas is unleaded, right? And they don't put lead in paints anymore. So they're trying to use other things. We're going to talk about batteries later. That's kind of a tough chapter even for me, but we're going to go over it. So they're trying to, take out cadmium and use metal hydrides instead, take mercury out of light bulbs and things like that. So that's getting rid of the hazards, okay? And then I left you with a lot of videos here if you're interested in that. So, but basically, when it comes to green chemistry, there are these 12 principles. And I'm going to go over them with the last slide. So these are your 12 principles. I stress here, one of the things is to use catalysts. And I sort of started talking to you about what is a catalyst in class. A catalyst is something that will make a reaction easier, won't require as much energy to run it. And we're going to talk about biological catalysts. Your body runs using biological catalysts called enzymes, right? And basically what they're doing is going to lower the amount of energy that goes into a reaction, make the reaction easier and more efficient to happen, okay? So talked a little bit about that in class. And then there's this video put out by the EPA. I showed this one in class. I think you should watch it again if you didn't see it, if you're interested and want to catch some points there. But it talks about what your governmental organizations are doing in terms of green chemistry. The EPA isn't just responsible for regulations, it's also responsible for greening chemistry and making alternatives to offer to industry to help their work be more efficient. And in the long run, if industry is more efficient, they make more money, so it's a win-win for them. Right. I brought this up for McGill. I like to also, again, dispense information in this class. If you're interested in this, again, this is a huge field, really burgeoning field. If you surely can get a job doing this. And McGill University is one of the top schools for this around this area. Of course, there's lots of American schools too, but they had a really nice video talking about one of the things that they push at that college or that university, and that is to use water as a solvent, which was really a big thing for McGill, and that's why I placed it here. So instead of using toxic chemicals, using water and basically floating your reactions on the water. So it's really cool. I didn't show this one in class, but I put it here so that if you're interested and motivated and looking for a field of study, this is a really good one. Now, so consider examples of green chemistry, right? We're going to think about some of these. Recycling, right? And what you can do to support green chemistry, right? So I'm going to go over the 12 principles. So waste prevention, right? So to minimize garbage and wasted resources that come out of that. And we're going to talk more about that later in the semester and how you get your atom economy, right? That's sort of related to here. So that's going to reduce waste by looking at your atom economy. Use less hazardous chemicals, safer chemicals in design, right? Use safer solvents and ancillaries. So for example, using water, right? More energy efficient reactions. And here comes back your idea of recycling. Use renewable, here I say feedstocks, this is in terms of making fuels, right? But try to reuse things like we were talking about with reusing iron from the cars, right? Reduce derivatives, so temporary things. Not all reactions just go forward as they are, so you want to try and reduce the number of reaction steps. Catalysis, as I said, one way of doing 8 is to apply 9, but catalysis, design things so that they will break down, not that they'll accumulate as waste and toxins in the environment. Real-time pollution prevention, so doing it as the synthesis is taking place. And then also trying to increase the safety of the chemistry that's taking place, right? So explosives and accidents and that kind of thing. So these are the 12 things that go into green chemistry. So it's a huge field, and you probably can get a sense of that, especially now we're trying to conserve our resources, make things more efficient, more profitable, and move away from things that you can't renew. So this is like I said, a huge deal, and I'm going to try to incorporate a lot of this as we go forward in the course. All right, so that's chapter 2. It's kind of like, again, it's a little bit more focused than chapter 1, but we're moving into our chemistry. I'm slowly getting you into these ideas, and hopefully that's going to help. And that's it for now.